The burning of organic matter, or biomass, has been used for the vast majority of human history to provide energy, whether it is to warm your feet and cook your food over a campfire, or by combusting wood and fossil fuels to drive electricity-producing power plants. When biomass is combusted, it releases a variety of gases, including carbon in the form of CO2, and to a lesser degree, carbon monoxide, or CO. However, it's possible to mechanically capture those gases that are released, preventing their escape back into the atmosphere. Additionally, there are a variety of methods that one can use to convert biomass into other energy or other products besides just combusting it, that can produce cleaner and easier ways to capture and use streams of carbon dioxide. The Roads to Removal report examines a variety of ways that we can use plants to remove CO2 from the atmosphere. Combined, forest management and cropland management could likely provide about 100 million tons of annual CO2 removal and storage in the United States. But there is another way that we can use photosynthesizing organisms to remove CO2 from the atmosphere, and potentially a lot of it. This is through a group of technologies that are collectively termed Biomass with Carbon Removal and Storage, or BiCRS. Sarah Baker from Lawrence Livermore National Laboratory and lead author of the BiCRS chapter in the Roads to Removal report explains.
BiCRS is Biomass for Carbon Removal and Storage, and this is an umbrella term that encompasses any approach that uses biomass or plants to capture carbon dioxide from the air and durably store it out of the atmosphere in a way that helps reduce the impacts of climate change. So this is a bit different, a broader term than historically what was known as BECCS, or bioenergy with carbon capture and storage, because we're taking away the emphasis on energy, because there are a whole lot of valuable things one can do with biomass for carbon removal beyond just making energy products. We analyzed 27 unique BiCRS pathways in the report, and then we ran an optimization tool to find the pathways that provided the most carbon dioxide at the lowest cost. And of these, a few pathways really stood out. And one of these was gasification of biomass to produce hydrogen. And another of these was pyrolysis of biomass to produce bio-oil.
Pyrolysis and gasification both use heat and pressure to break down organic matter without actually combusting it. In each of these processes, carbon dioxide can be separated out and then transported to a region with suitable geology for deep, permanent underground storage. The other products can be used to replace traditional fossil fuels in areas that are hard to decarbonize, such as in shipping, air travel, or heavy industry. The Roads to Removal report examined two aspects of these type of BiCRS technologies: how much CO2 could be removed in the United States, and what might standing up these technologies look like. Here's Dr. Sarah Baker with the good news first.
I'd say the biggest takeaway from our chapter is the enormous impact that BiCRS could have if we build it out in the United States. We found that BiCRS could really have among the highest impact on carbon removal because of the amount of carbon that could be removed with BiCRS at a cost of less than $100 per ton.
Dr. Baker and her colleagues found that more than 800 million tons of CO2 could be removed from the atmosphere every year with BiCRS, at a net cost of less than $100 per ton. But unlike forest and cropland management, this kind of removal is not ready to go tomorrow. That is because the logistics of building out a BiCRS system is complex. First, you need a sustainable source of biomass, which could be waste, such as from strategic forest thinning to reduce wildfire risk, or municipal waste, or agricultural waste like corn husks and nutshells. Here's Dr. Baker again, along with her Roads to Removal colleague, Dr. Curran Scown of Lawrence Berkeley National Laboratory.
The largest source of concern about deploying BiCRS in the world has to do with what is called land use change. Most of the biomass that we're looking at in our report had no land use change. It was only looking at waste biomass.
When we started digging into what this looks like when you start growing carbon crops across the US, we realized that there was a lot of land that's available to grow these crops on, and it might not be the highest yielding land, right? Some of it is cropland that comes in and out of production. It's not the most attractive land for agricultural production. But if you can grow something like switchgrass on it, especially if you start co-locating that with renewable energy, you've totally transformed that landscape in a very positive way. And you can do this without needing to irrigate.
Dr. Andrew Wong of Lawrence Livermore National Laboratory helped analyze regional patterns in resources and removal capacity for all carbon removal strategies examined in the report.
How can you take biomass or grown material, transport it, and where can you store it? So those three factors of growth, transportation, and storage are really key factors when we think about BiCRS. And the area of the country is the upper and lower Midwest. Huge amounts of agricultural growth. This is the breadbasket of the country, as well as being adjacent to some of the best geologic storage capacities in the country.
Since BiCRS offers such a huge opportunity to pull CO2 out of the air, the report authors also wanted to examine how it could be implemented in an environmentally just way. Dr. Kimberly Mayfield, also from Lawrence Livermore National Laboratory, examined how energy equity and environmental justice played into where and how BiCRS could most effectively be developed.
You're really looking at two different opportunities when it comes to energy equity and environmental justice. One of them comes from the side of where the biomass is being collected from, right? So this biomass is not sitting there being a resource that people are dying to get their hands on. It is currently being treated as a waste. Sometimes it's being burned, sometimes it's just being scattered over fields, sometimes it's being landfilled. And what we are trying to do with the Roads to Removal report is analyze what counties in the United States are currently facing the most pollution issues associated with these biomass stocks, and where can we transport them away from to reduce the pollution burdens on those local communities. And then from a facility side, this is where the facility is going to be located that's actually going to take that biomass and convert it into the CO2 or the hydrogen, the end product. And there, similarly to direct air capture, you are looking for people who have the skills to pull a large facility off. You're looking for the people that are skilled in construction, plant operations, oil and gas extraction, mining, waste management. You're looking at a diverse set of skills that is able to take the diversity of biomass waste from the United States and convert them into usable resources that are really important for decarbonization overall.
There's the potential and there's the opportunity to be able to pull a gigaton of carbon dioxide out of the atmosphere in actionable ways with technology we have today. That was kind of surprising because frankly, sometimes the problem just seems really daunting. And it's almost like it's a big thing that other people have to think about. But really, if you look at it, there's collective effort that's needed, but it's possible.
To learn more about the diverse approaches available for carbon removal in the United States, or to download the report, visit roadstoremoval.org.